A linear combination of matrices. Here's a matrix C of size 2 by 3. Here's a matrix D of size 2 by 3. In order to add a linear combination of these two matrices, they have to be the same size. If they're not the same size, we cannot add or subtract matrices. It does want you to find this expression. Find the expression -4 scalar multiplied to C minus 5 scalar multiplied to D. Why don't we write this expression out and manipulate it, and let's see what happens. -4 times matrix C minus 5 times matrix D is equal to -4, 6, 0, 6, 1, 6, -4. Then we're going to subtract 5 scalar multiplied to 4, 0, 1, -2, 3, 6. And remember, subtraction really just means add the opposite. Subtraction is not really an operation. So you can think of subtraction as adding the opposite. What we're going to do now is simply absorb those scalars. We're going to absorb those scalars. Those -4 get sucked into the matrix like a sponge. This -5 gets sucked into the matrix like a sponge as well. I might just absorb the 5. Let's see what we got. We have -24, 0, -24, -4, -24, 16. Notice the size of the matrix is still 2 by 3. Minus 20. We got -10. And then we got 0. We got 5, 15, and then 30. And now the matrices are still of the same size, so we can certainly add the opposite or subtract. And what do we get? We still get a 2 by 3 matrix, but now we have -44, 0, -29, let's see, 6, -39, and we have -14. And there you go. You found the expression -4C minus 5D. I'm going to put a period here, and I'm going to circle the final expression. Multiplication of matrices. There's a matrix A of size 3 by 3. There's a matrix B of size 3 by 2. And this is a separate example. We'll look at example B a little bit later. It says find B times A if it's defined. This is really weird for mathematics. Usually, if it's mathematics, it should say if the product is defined, find B times A. You really should see it like that. It's better to read if-then statements. If BA is defined, then write out B times A, right? If the product is actually defined, then we write out B times A. The first thing we're going to do is I'm going to write B first. We want to actually arrange our charts or our matrices in the right order. In the order of interest, in other words. We're trying to see if B times A is even defined. And the way you know matrix multiplication is defined is that for the first matrix, the number of columns must match the number of rows in the second matrix. So one way to illustrate this is simply looking at the size of the matrix. So B is 3 by 2, and A is what? A is 3 by 3. Once again, the way matrix multiplication is defined, the number of columns of the first matrix must match the number of rows in the second matrix. So we're checking this. Remember that 2 is the number of columns of the first matrix. And this first 3 is actually the number of rows of the second matrix. Well, does 2 match with 3? And the answer is no. These do not match. So I'm going to write don't match. Therefore, BA is not defined. And I'm going to circle that as the final answer. In other words, that expression is not defined and it does not exist. Why don't we look at AB though? Now I'm going to look at AB for example A. So I'm going to take this here and let's see if is A times B defined. So if you look at that, you first have a 3 by 3 and then we have a 3 by 2. And sure enough, it is defined. And not only is it defined, but you also know the size of the outcome. So you want to first check this. That matches. And that tells you A times B is defined. And so yes. Not only do you know that it is defined, you even know the outcome of the size. The outcome of the size is actually 3 by 2. In fact, A times B has size 3 by 2. And you could see that by looking at the numbers. Let me try to convince you here of what just took place. So remember, this was matrix A. Matrix A had size 3 by 3 and matrix B has 3 by 2. So the first thing you want to do is make sure if this matches. If this matches, then AB is defined. So that's the first thing. The second thing is, if that matches, then you proceed to finding the size. The size of A times B is actually 3 by 2. And if you wanted to find the size of A times B, I will give you a hint. Let's see here. So if you rewrote A, I'm going to highlight 3, 1, negative 6. And then I'm going to write the rest. 7, negative 2, 7, 3, 1, 0. And then I'm going to write B as well. B is I'm actually going to write this a little bit differently. I'm going to leave A like that. I'm going to write B next to it. B is, I'm going to write it this way. 6, 5, 5. And then 6, 1, 1. And so you know the output has to be a 3 by 2 matrix. And the way you get that first entry of that 3 by 2 matrix is multiply 3 times 6, and then add it to the multiplication of 1 times 5, and then add it to the multiplication of negative 6 times 5. And if you do that really quick, let's see what you get. 18 plus 5 is 23. 23 minus 30 is negative 7. So in that first position, you should get negative 7. If you want me to finish this, I usually do the row first. So the row here, 3, 1, negative 6. And if we want to get this position here of the 3 by 2 matrix, we take this 3, 1, negative 6, and we're going to multiply it to 6, and then add it to 1 times 1, and then add it to 1 times negative 6. Let's see what you get. 18 plus 1 is 19. 19 minus 6 is 13. So right here is 13. I'll leave it up to you to finish this. For the second example here, example B, I'm going to give you a hint. You find AB if it's defined, or if the product AB is defined, find its product. Let's first check the size of A. It's 3 by 1. And let's check the size of B. It is 1 by 3. So this is definitely defined. This actually matches. Awesome. Okay, that was the first thing. And the second thing is, you know the size of A times B as well. AB is 3 by 3. So make sure you have 9 entries in your matrix A times B. I'll let you compute those 9 entries, so you might want to pause the video right now and go ahead and attempt to manipulate the expression A times B for part B. And pause the video, and when you unpause, you're going to realize I'm going to reveal the answer for you. Just make sure you actually get the right answer or get the same answer. First entry is 2, second entry is -8. And there is the actual answer. Make sure you can get that. So you definitely want to think of matrices as tables of data. Some of you may have used Microsoft Excel, and of course if you use an Excel spreadsheet, you're also making tables of data. The advantages of working with matrices is sometimes you could organize the information where you could actually put an operation called multiplication, and then you could move that information. And when you move that information, sometimes it has a very purposeful meaning. A very purposeful meaning. Let's look at it through this example here. Mary owns 3 sidewalk food stands. One is in Tomsville, one is in Newton, and one is in Glen City. Each stand sells hot dogs for $1.20 each, candy bars for 70 cents each, and bags of chips for 60 cents each. The stand sells nothing else. In one day, the number sold for each type of food at each location was as follows. So here's a table of the number of items that were sold in each different city. And there it is. With a matrix, you simply convert it with brackets, and then you arrange the data in a very, very specific order. Okay, order matters. Find a matrix B whose entries are the prices in dollars of each type of food. Make sure the product B times A is defined, and its entries are the amounts of money in dollars made at each location overall. So we're going to define a matrix B, and my hint to you is actually first write out A. I'm going to write A over here, 390, 410, 430, 590, 600, 650, 510, 470, and then 460. So I'm just rewriting matrix A, and we need a matrix B in front of it. And remember, when we do B times A, we need to make sure that for the multiplication to be defined, the number of columns in matrix B will also have to be 3. It makes sense to make sure matrix B is 1 by 3. And what 1 by 3 matrix does that have to be? Well, we need to put the price of a hot dog first. What's the price of a hot dog first? $1.20. And then in the second entry, we need the price of a candy bar. which is 70 cents, and so on, and 60 cents for a bag of chips. And if we do that, we could actually arrange the data and move this computation to give you the total revenue, okay, or the total amount of money taken in. So matrix B here, I'm going to write it in this box. Make sure you write it on your own paper. You don't ever want to type an answer in without writing it on your paper first. And we could compute the product B times A as well. Let's move this expression. Let's move the data. You can certainly use a calculator here. So when you actually move the data, notice you're going to get a what? You're going to get a output of 1 by 3. So B times A is 1 by 3. That means 1 row and 3 columns. For the first position, I got 1187. For the second position, got 1194. And for the third position, got 1247. And I'm going to just put a note outside here just to remind myself of the units. And that is, this is actually in dollars. So how do we compute the total amount of money? We simply add up all 3 of these numbers. The total amount is what? 1187 plus 1194 plus 1247. I guess I could write it sideways. And of course, you could put that in the calculator. Let's see what that is. That amount is 3628. And of course, that is in dollars. Once again, just make sure you actually write the units on your own paper before you type in any answers. I guess I could circle all the final answers. And there you go. Matrix multiplication could actually move data and make sense of it rather quickly. Finding the inverse of a 2 by 2 matrix. Here's a matrix A. Find the inverse of A if it exists. Once again, this isn't the greatest mathematical grammar. It should say if the inverse of A exists, state what it is. State the inverse of A. I guess I could change that to an if-then statement. If I'm talking about very, very proper mathematics, then state the inverse of A. We're going to go ahead and find the inverse of A. I'm actually going to use a technique called the Gauss-Jordan technique. Or sometimes it's called the Gauss-Jordan elimination. Gauss-Jordan technique. And what this does, it is a trial and check method where we're looking for a very, very specific row reduction. The Gauss-Jordan technique goes something like this. You take your A, you take your square matrix A, augment it with the identity, with an n by n identity, then you perform a bunch of elementary row operations. And if you get an identity on the left and augmented with a matrix B over here, then the conclusion is that B is in fact the inverse of A. And that's what we're going to do. We'll take the matrix A, augment it with an identity. So your first matrix is going to be size. What's the size? Think about it. Augment it with the identity. So your first matrix is actually of the size 2 by 4. Let me draw that line dotted because I think that's what your textbook uses or your software uses. And now we're going to row reduce. And we're going to row reduce in such a way where we want this as the outcome. We want the identity on the left-hand side, and then whatever you do with the row reduction, hopefully it yields a matrix on the right-hand side of that augmented line. I guess to be consistent, that should be dotted. Let's make that a dotted line. Dot, 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 dotted line. It's the same dotted line over here. Okay, let's get that leading 1. First thing I notice is I could do row 2 added to row 1. And if I draw that arrow, that means row 1 changes. Row 1 gets the new storage. Now row 2 doesn't change, so I'm just going to copy it over again. And we're going to change row 1 now. We get a 1. And we get a 1. Row 2 plus row 1 and a 1. Oh, that's convenient. Now we would like to get a 0 right here using elementary row operations. We're going to go ahead and scalar multiply row 1 and add it to row 2. What are we going to scale multiply by? We're going to go 3 times row 1 added to row 2. And if I draw that arrow from left to right, that means I'm going to store in row 2. If I store in row 2, that means row 1 doesn't change. So I just copy it over. Now we get a 0 here. And we get 3 times row 1. So 3 plus a -4. -1. 3. And then a 4. Nice. Now we get negative row 2. We could scalar multiply a single row. And I'm going to store in row 2. Remember that tilde means row equivalent. Row 1 doesn't change. I'm going to recopy that. And we get 0 now. 1, -3, -4. We would like this position to be a 0 using an elementary row operation. So now I'm going to do negative row 2 added to row 1. And we get 0, 1 for row 2. Row 2 doesn't change, so -3, -4. And we get a 1, we get a 0 here. Now we got 3 plus 1 is 4, and 4 plus 1 is 5. Aha! Notice, on the left-hand side of this dotted line is the identity matrix. What does that mean? That means we actually did find the inverse of A. The inverse of A is over here. So let's make our conclusion. Therefore, the inverse of A is indeed going to be 4, 5, -3, -4. And one way to check, I'm going to leave this up to you. If you don't believe that's the inverse, you could check this. I'm going to let you check it. You check what A times the inverse of A is, and as a separate check, you're going to do the inverse of A times A. So if you multiply these two sets of matrices, you should get something very, very interesting. So why would anybody find the inverse of a matrix? Well, one application involves solving systems of linear equations. Here is a system, 4x plus 5y is equal to -1/2. And you know that graph's a straight line. Here's another straight line, -3x minus 4y equals 1. want to go ahead and use matrix multiplication to try to solve this system. I'm going to give you a little bit of insight here. One way to rewrite this system is to write it like this. You could actually write a matrix like that, and that is 4, 5, -3, -4. This is often called a coefficient matrix. Then you can multiply it by a 2×1 matrix called x comma y. And then it has to equal, let's say, the constants on the other side. So this is another way of writing a system of equations, is in the form of matrices. Now, in order to solve this, it would be nice to find, let's say, the inverse here. So 4, 5, -3, -4. It would be nice to find its inverse. That is not an exponent. That's called inverse notation. That is just a notation for inverse. Keep in mind that -1 is not an exponent. In this context, that is not an exponent. I'll say it again and again and again. In this context, that symbol just means inverse of. It is not an exponent. And if you're balancing the equation, then we have to write it over here as well. 4, 5, -3, -4. And we need the inverse of that matrix. And then what are our scalars here? -1/2 and 1. And if you do that, this right here is called the identity. The identity here, or I sub 2. Let me not use I sub 2. Why don't I explicitly write it out? The identity matrix will look something like this. And if you multiply the identity to x comma y, you simply get x comma y. And then over here, you get, hopefully, the answer to your system of equations. Now remember, that's not an exponent. That just means inverse of that matrix. So that's what's going on. Notice when you multiply this, that just gets you x comma y. So the key here is to actually find the inverse of that particular matrix. And one way to do it is use Gauss-Jordan technique, where you augment it with an identity and then row reduce and hope it all turns out just fine. There is another way to find the inverse of a matrix. And it's actually a formula. And to save time, I'm going to go ahead and introduce that formula. So let's say if you're given, well, let's say if you have a matrix A that equals, let's say, A, B, C, D, with 4 constants in those 4 positions, and AD minus BC is not equal to 0, then the inverse of A can be given with this formula. It is 1 over AD minus BC times the matrix, switch the A and the D and negate the B and the C. And that is now the inverse of A. That is a really, really cool formula that comes from a subject called linear algebra. For our specific case here, we could see that A times D is -16, and subtract B times C, which means add 15. So that's just -16, add 15, which is -1, and -1 is not 0. So we're in good shape here. Using the formula here, I'm going to go ahead and use that formula and find the inverse of A. So the inverse of A is equal to 1 over what? 4 times negative 4 minus 5 times negative 3. That's really key. That is not 0. That is not 0. In fact, that's negative 1 in the denominator. That's negative 1 in the denominator. Now what we're going to do is switch the A and the D positions. So I'm going to switch negative 4 and 4, and we're going to negate negative 5 and negate negative 3, so that would become positive 3. Now, that coefficient is actually negative 1. This coefficient here is just negative 1. Let's absorb the negative 1 in to get our inverse of A. If you absorb the negative 1 in, we simply get our inverse to be 4, 5, negative 3, negative 4. Alright, so in this box here, it seems silly, the formula is given like this. xy is equal to the inverse of A times the other matrix, which is negative 1/2, 1. So right here, you're going to write 4, 5, negative 3, negative 4, and then this matrix here has got to be the size 2 by 1. And you could do that to compute x's and y's. So the x is going to be what? The x, notice it's 4 times negative 1/2, which is negative 2 plus 5. So that's a 3. That is a 3. And then let's find the y values. Negative 3 right here. So 3 halves minus 8 halves. What's 3 halves minus 8 halves? 3 halves minus 8 halves. 3 halves minus 8 halves. Negative 5 halves. So this should be negative 5 halves. Now I don't like to write the answer like this. It's better to write your answer as a solution set. So use a set brace. This is a set consisting a unique solution, and that unique solution is an ordered pair. It just says that the two straight lines intersect at an ordered pair, or at a single point. So this is a set consisting a unique solution. That's how we describe this. Let's circle our final answer. Write solutions to 3x3 systems of linear equations from augmented matrices. Two augmented matrices for two linear systems in variables x, y, and z are given below. The augmented matrices are in reduced row echelon form. For each system, choose the best description of its solution. If applicable, give the solution. Here's a row-reduced augmented matrix in reduced row echelon form. Now, you're not in 2D anymore. If it says x, y, and z, you're in 3D. So this is a computation involving 3 dimensions already. And you haven't really studied too much of 3 dimensions, with the exception of volume. I'm going to remind you this, though. This is x, y, and z. So these columns represent the variables x, y, and z. But the 1 and 2 are only the coefficients in front of it. So I just want to remind you that this is a system of equations. It just says x plus 2z is equal to negative 1. It also says what? Y plus z is equal to negative 2. And then the last equation is the obvious. 0 plus 0 plus 0 is equal to 0. Well, that's, in other words, the last equation on the bottom of this matrix is actually information that's not new. Even given all this information, we read things going up. So there is a free variable here, and the free variable is going to be z. So notice I'm going to let z run freely. It's going to be in the set of reals. So let z be in the set of reals. And then we're going to go up and solve for y. So if we go up and solve for y, we get y is equal to negative z minus 2. And we also get x. X is equal to negative 2z minus 1. And that's all we're looking for here. So I'm going to choose this third bubble here. I'm right here. I'm choosing this third bubble here. I like to pick on z because you should read the system of equations from bottom to top to really understand this. Back substitution. We call it back substitution. To really understand the back substitution, you read it from bottom to top. Okay, always read it from bottom to top. Don't read it from top to bottom. You'll get into all kinds of trouble. I also don't like the way your software decided to write the answer here. It's not a good way of writing the answer. So what we're going to do is take advantage of mathematics. The beauty of mathematics is there's something called set builder notation. So we're going to write a solution set. And the solution set is going to be the set of all ordered triples such that the first component is negative 2z minus 1, comma. The second component is negative z minus 2, comma. And then the third component is z, such that z is in the set of real numbers. In other words, there's an infinite number of solutions here. Remember, how do you read that vertical bar? That's such that in set builder notation. So that's for part A. I could definitely circle that answer for part A. Circle, 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 circle. Here we go. Let's do a second example. Part B is a little bit more straightforward. I do want to remind you that you still should read up. In other words, if you read up here, that says z equals 2, y is equal to negative 1, and then x equals negative 3. And of course, we could write our set consisting of a unique solution. So our set here consisting one ordered triple. So a set consisting a unique solution, or one ordered triple. There it is. And that is the answer to part B. You can circle that. So here's a matrix representing 3 variables, and it's actually a system of linear equations where the unknowns are x, y's, and z's. And let me remind you where they are. The first column could be x's, the second column is y's, and the third column is z's. So this matrix is actually telling you a lot of information. We do want this in reduced row echelon form, and there's many ways to get there. There's more than one way to get there. So before I actually start reading the data, I'm actually going to try to row reduce this and try to get more information out of it. The first thing I'm going to do is actually switch row 2 with row 3. This is now row equivalent to 100 is the first row. I really like that because we want the leading 1 to be in the upper left-hand corner. We're going to switch row 2 and with row 3. I'm going to switch row 2 and row 3. And let's try to get another leading 1 in row 2. And the way we're going to do that is simply take 1/4 of row 2 and then store in row 2. That is now row equivalent to 100, 4, 0, 1, 0, and then that's negative 11 thirds. And then we have negative 3, 1, and 0, and negative 47 thirds. Now that is strange. That actually, if you look at this carefully, this third column has a column of zeros, and that is very unusual. I do want a 0 here. It'll be nice to get a 0 here as well. Let's see if it's possible. I'm going to do 3 times row 1 and add it to row 3. So now we're just going to store in row 3. Tilde is the row equivalent symbol. Row 1 doesn't change. And then we have row 2. Row 2 doesn't change. What we are going to attempt to change is row 3. So that's a 0. That is a 1 still. And that is a 0. And then 12, add it to row 3. So 12 is 36 thirds. And then that is negative 11 thirds. Ah, interesting. Now we're going to do negative row 2 and add it to row 3. And now row 3 changes. Rows 1 and 2 does not change. And then this is now a row of zeros, which means no new information on that bottom row. Remember how to read these matrices. When you're solving systems of equations, we read from the bottom up. So this says Z is free, Z is in the set of reals, Y is very specific, and then X is very specific. So what is our infinite set of solutions? Or I should say the set of infinitely many solutions. We have a set of ordered triples such that the first component is 4, the second component is negative 11 thirds, and the third component is Z, such that Z is in the set of reals. Remember that. How do you reread that? We read that as such that. If there's an infinite number of ordered triples that satisfy this system, could you pick 5 of them? Could you state 5 of them on your own? Go ahead and write that on your paper. Go ahead and state 5 ordered triples that will satisfy this system of equations simultaneously.